Okay, so today we are going to do our lecture 15. This would be a continuation of things that we were doing earlier, the four fundamental subspaces of a matrix. So we had already talked about the so-called null space, which was denoted by n of A. Then we started discussing the so-called column space, which we would denote by C of A. And there were two more spaces that we want to deal with: row space and the so-called left null space. Okay. The idea is, once you get to know all these four spaces, you have a lot of information about your matrix A or the linear transformation A, how it is going to behave and stuff like that. Row space of A also has a notation. For now, we will just say it is the row space of A. And for left null space, well, for reasons which is not obvious right now, this would actually be the null space of A transpose. Okay, this is how we are going to define it. Okay, so first things first, when we said A is a m by n matrix, then that means it represents a linear transformation and I will use the same name for the linear transformation, it's just easier. From some vector space to another vector space. We have to be very clear about the dimension of this. A is a m by n matrix, so it has m rows and n columns. So this would be matrix linear transformation from, question is what should we put here, m or n? So think of it this way, it's a confusion which students generally have. If I have m rows and n columns, so let me just put m rows and n columns. The vector with which you can multiply possibly, so it's a m by n matrix. So the only vector you can multiply by is a n by 1. So the input it can take is only from Rn. And the output it will produce would be in Rn. So it represents a linear transformation from a n-dimensional vector space to a m-dimensional vector space, R into Rm. And there are certain things that we should be very, very careful about. Where do these spaces live? So for example, what about the null space? The way we had defined null space, it was all those vectors x in the domain. So in this case, it is in Rn, such that A would map this vector to the zero vector of Rn. So this means this is living inside Rn, and we had shown that it is a subspace of Rn. Okay. Now, how did we define the column space? We said things belong to the column space if it is a linear combination of the columns. As you can see, the columns, they all live in Rm. So their combination will also live in Rm. And we said all those B's for which this is a consistent system. So for obvious reasons, this will live in Rm. So we should be very clear where these guys are living, because that is a source of confusion as well as something that we have to be concerned about. I make a small claim that this is a subspace of Rm. So the column space is also a subspace, but this time it is a subspace of something, or I should say it's a subspace of the codomain. Okay, why is it a subspace? Let me get rid of these things first so that understand this a bit better. Okay. So question is, why is it a subspace? Now, the answer is fairly straightforward if we recall one of the results we had proved about subspace. We said any time we have a linear span of vectors, if we have a linear span of a set of vectors, it is always a subspace. This was a result we had proved when we were discussing the linear span. And so based on that, we can say that since column space of A is nothing but the linear span of columns of A, it's definitely going to be a subspace. And for reasons which are now clear to us, then it would be a subspace of Rn, because the columns of A live inside Rn. So the idea is basically that this is an easy way for us to get if something is a subspace of space, if we know that that something can be spanned by a bunch of vectors, or it is actually the linear span of a bunch of vectors. So question is, where do we go from here? We will first try to figure out how to compute column space of a matrix, and then we will try to deal with other stuff regarding the column space. Okay. Now, in order to do that, let me first start with a very simple matrix where things might be slightly obvious, and then we'll go to something where things might not be that obvious. So here's my example, a simple example, just to see if we can play with things or not. So here is my matrix A. Let's say I gave you 1, 2, 3, 2, 4, and 6. Okay, so here's my matrix A. As you can see, it's a 3 by 2 matrix. So you can view A as it's a 3 by 2 matrix, 3 rows and 2 columns. So you can view it as a linear transformation from R2 to R3. Okay. So we know that whatever is the null space is going to live inside R2. And we know that the column space would live inside R3. Okay. So these are things which we have gathered so far. But question is, what else can we say about the column space and the null space in this particular scenario? For example, if I want to compute the null space, here is a small claim that I make and see whether we agree with this. We can say 0, 0 belongs to null space because 0, 0 will always map to 0, 0 in the column in R3. What about another thing? How about this? Can we say this vector belongs to the null space? Now, one may ask, how do I know that this particular vector will work? If you look at the entries, the second column is actually twice the first column. So if I claim that this belongs to the null space, then all I'm claiming is that 2 times the first column minus 1 times the second column will give me the 0 vector in R3. So that is why I was able to sort of guess the solution without really going through full-blown thing. So we know that 0, 0 belongs to this vector, 2 minus 1 belongs to this. So we ask ourselves, what are all the vectors that belong to the null space? Remember, your null space is in R2. Since it is a subspace, there are only few possibilities about it. The possibilities are that either it is the 0 subspace, or it would be a space spanned by one single vector, in which case it will be a line, or it will be a subspace spanned by 2 vectors. Now, since we are living in R2, if there is a subspace spanned by 2 distinct vectors or linearly independent vectors, then it has to be entire R2. So we want to know whether it is 0 subspace, whether it is a line, or whether it is entire R2. We have some evidence. It can't be just the 0 subspace because we know we have found this vector which belongs to the null space. So either it is a line or it is entire R2. Could it be entire R2? Well, if it was entire R2, then every vector can be sent to the 0 vector. But for example, if you see, if I change the linear combination from 2 and minus 1 to, let us say, 1 and 0, it won't map to the 0 vector. So for sure we know that the null space cannot be entire R2. So let me make sure that the null space is not entire R2. Because, for example, the vector 1, 0 does not belong to the null space. So we are now convinced that it is only a line which passes through the origin, and it is along the vector 2 minus 1. So when you say along the vector 2 minus 1, so it would be, say, something like a line which passes through this point 2 minus 1. So we claim that this is the null space of my matrix A. So anything which lives on this line, imagine if I had tried to make a 3-dimensional space, anything which is lying on this line gets mapped to the 0 vector over there. Okay. So everything which lies on this line is a null space. Another question is, what about the column space? What all things can I hit over there? Now, column space lives in R3, so I have to find out things which live in the column space. Let's go for some obvious creatures first. So this time we are going to talk about the column space. Now, what about the column space? Well, let's go with obvious solutions first. Look at the definition of column space. Didn't we say column space is basically a space spanned by columns? So, for sure, the first column and and the second column, for sure these guys will live in the column space, because the definition says anything that you can make up of these two columns will live. So of course you can make each of them individually. Now comes the bigger part. What else can you make out of these two columns? Now, when you say what else can I make out of these two columns, one thing is for sure, that this column 2, 4, 6 is a multiple of the first column 1, 2, 3. So whatever 1, 2, 3 can make, let me put it different. Whatever 2, 4, 6 can make, would you agree the vector 1, 2, 3 will be able to do it on its own? So if I look at the linear combination of A, 1, 2, 3, plus B times 2, 4, 6, it's actually nothing but a multiple of the vector 1, 2, 3. So anything which lives in the column space of the matrix A is going to be a multiple of the vector 1, 2, 3. So if we come here, if we look at what we are able to accomplish here, it would be basically a line which passes through origin and is in the direction of the vector 1, 2, 3. So I won't make an attempt to draw a perfect line, but imagine it's this line which is basically representing the column space of A, which is basically all multiples of the vector 1, 2, 3. So what this is telling you is, if you pick any point in here, if I pick any point in here, and if I try to take its image under the mapping A, it would be on this line somewhere. Okay? So here's a question that one may ask. I said that this point maps to, say, some point there in the column space. If I focus my attention on that point only, I focus my attention on this point, one may ask, okay, what are the other things which could possibly map to that point? You gave me one solution. Are there other solutions? So here's a question. Let me first write it down so that we are at least clear about some things. So let me call this point as some B0. So if B0 belongs to the column space of A, then we know there must exist a X0 in R2. Such that A of X0 will give me B0. This is what we have found so far, that there exists a X0 which would map to that B0 over there. Question is, are there other inputs in R2 that can map to B0? Question is, what are those inputs and where would they map? Okay. How do we find any of them? So that is where the things become very interesting. How do we find all of those guys which would map to the point B0? Now, if I give you the algebraic solution, it's fairly obvious that we will be able to understand what that would be. However, let me try to convince you geometrically. How is this possible? What I will do is I'll take this null space and I'll shift it parallelly so that it passes through the point X0. Okay? So this is basically, you can think of it as X0 plus the entire null space shifted by the vector X0. So I took this line and now I've shifted everything by this vector X0. I claim that any point which lies on this line X0 plus NA, or the shift of NA by X0, everything on this line would map to B0. Now suppose for a moment assume that was true. Then would you agree null space holds the information about all possible solutions of a given system of equation? So the question is, why am I so sure that this will work? Well, let's try. If I find anything in the null space added to x0, I claim that it would give what I'm looking for. Okay. So here's my answer to this question. And that tells us the significance of the null space in this entire context. And why we are so hung up on null space. Okay. So let us consider a point x0 plus xn, where xn is coming from null space. Okay. So for example, if you take an xn here, you do a parallelogram law, you will get a point which lies in here, which would be of the form x0 plus xn. Then let us consider what will happen to ax0 plus xn. By the linearity, this will be ax0 plus axn. ax0 is b0. axn would be the 0 vector because xn belongs to the null space. Hence, this vector maps to the b0 vector. So anything which lies on this translate of my null space will give me a solution to that equation. So what it tells me is, if you can find me one linear combination which can produce me the vector b0, then depending on my null space, I may be able to find you infinitely many such combinations which would give me b0. Okay? But there is one point that we should keep in mind out here. Assume, again, we have not proved concretely everything, however, we have enough evidence that the null space can be only a line. And regarding the column space also, we have enough evidence that it can only be a line. Now, whatever notion we associate with the dimension of a vector space, even though we haven't described what is a dimension, but whatever notion, geometrical idea we have grown up with, on that basis, I can say that the null space is one-dimensional. It's a line. Likewise, the column space is one-dimensional. It is also a line. And what is the sum of these two dimensions? 1 plus 1 is 2. So what is so significant about it? Let's see what is the total dimension of the space where everything is starting. R2, it has dimension 2. Could it be that the dimension of the null space and the dimension of the column space will always be equal to the dimension of your domain space? Could that be true? And if yes, why should it be true, and what is the significance of it for us? As it turns out to be, we will show that this result would be true. That the dimension of the null space plus the dimension of the column space will be equal to the total dimension of that space you start with. And as we proceed, we will see it's fairly intuitive, if not obvious. However, proving it requires a little effort. However, from geometrical perspective, it is not a totally surprising result, I should say. Okay. Now, before we proceed further, I want to make some changes and see if things can be made slightly differently. Can I change this matrix so that my null space changes without changing the column space? Can that be done? Right now the null space is this line. Can I change the null space somehow without changing the column space? Or what if I want to keep the column space the same? Can I change the null space? Can we manipulate these things with the matrix or not? So for example, if I add one more row to A, what effect would it have on the null space of A? So I'll give you an example and you will see what happens. I'll make a small change in this A, and I would like to see if it will have some significant effect or not. So what I'm going to do is, I'm going to introduce a small change in my matrix A. So I'm going to add another entry. Let me put a 0 here and let me put a 1 here. Okay, so now I have changed my A from a 2 by 3 matrix to, a 3 by 2 matrix to a 4 by 2 matrix. So of course things have changed. What is the null space? Can I say, let me make some changes here also. So it's a new example you can say, but built upon the old example. So let me avoid confusion and let me give this matrix a new name. I'm just trying to show you how you can make examples work in a way that you want them to. Okay. So let me call this as matrix some L. I don't know if I should call it L. That's okay. Let's call it L. So L is a 4 by 2 matrix. So now this is from R4 to R2. Oh, I'm sorry. R2 to R4. It's like 4 by 2. I still have it. So from R2 to R4. Now as you can see, the input space has remained the same as the previous example. The output space has changed. Question is, what happens now? Okay. We proceed. Yeah. Yes. So now the question is, okay, so what are the changes that we will get if I make a small change like this? How will it affect the null space? Now, null space this time is again going to sit inside R2. And the column space this time will sit inside R4. Remember last time what had happened? Null space was a line, column space was also a line. This time by adding this vector, what will happen? What will change? Now as you can see, the way I have given this matrix, the first column is not,
Tape is not adhering.
so the first column will not be basically a multiple of the second column or vice versa. So things out here are sort of linearly independent. So if I go for null space this time, obvious vector for null space is definitely the 0, 0 vector. Question is there something else which could possibly give me a 0, 0 combination? Now, from our ideas of linear independence, column 1 is linearly independent from column 2. And why is it so obvious? Well, these are two columns. If they were dependent, they should be multiples of each other. And as we said, they are not multiples of each other. Another way to look at it is the first column has a 0 in the last entry, and the second column has a non-zero entry in the second column. So how can they be multiples of each other? So we know that these are linearly independent columns. So that means they cannot produce a 0 vector except when we combine them trivially. So then we know that 0, 0 is the only vector in the null space. So this tells me that the null space of A consists of only the 0, 0 vector and nothing else. So this time, the dimension that we perceive of the null space is 0. There is nothing except for the 0 vector. What about the column space? Well, again, by linear independence, it is kind of clear that column space is spanned by two independent vectors. So column space is spanned by two independent vectors. So this means that whatever this guy is, it would be definitely a plane, a two-dimensional plane in R4. So again, the sum of the dimensions of the null space and the column space turns out to be equal to the dimension of the domain space. So it can't be a coincidence, but you see, by a small change in the matrix, we were able to change the null space quite a bit, and it also affected the column space as such. Okay, let's see, could we have made another change in the matrix and got something different out of it? So I'll do a third example based on our original matrix. This time I'm going to make a change in the columns of the matrix and see what happens. So here's my third example. So here's my matrix. Let me see what name should I give it. Let me call it as S. So remember, this was my original matrix 1, 2, 3, 2, 4, 6. I'll make one more change and see something happens. Let's see if we can add another column to it. This time, it would be a linear transformation from R3 to R3. Let's see what are the null spaces. What is the null space of this? I should call it the null space of S instead of null space of A. So what about the null space of S? Okay. Let me go with the obvious candidates. Can I say 0, 0, 0? Definitely belongs to the null space. What else can I say? Can I say a vector like 0, 0, 1 will also belong to the null space? The significance of this last one is that even though I may make the first two columns 0, but I can put any non-zero element in the third column and have a linear combination which still maps to 0. Do you remember the original solution that we had? 2 minus 1. And here I can put anything I want. For example, I can put 2 minus 1, 0. That will also be a solution to this equation. That vector will also live in the null space. Okay. Now, imagine I told you that these two vectors live in the null space. Does everything live in the null space? For example, does the vector 1, 0, 0 live in the null space? The answer is, of course, no, because if you look at 1, 0, 0, 1 times the first column, 0 times the second column, 0 times the third column doesn't produce me the 0 vector. So we know that whatever is the null space, it cannot be three-dimensional because we have vectors which do not live in the null space. We know it has to be at least one-dimensional because at least a non-zero solution is there. We can also say it is two-dimensional because we have two linearly dependent vectors, both of which belong to the null space. So in a sense, we can say that we have a plane in R3 which would be the null space of this matrix. Question is, what about the column space? Now before we proceed, suppose that result was true, that the sum of the dimensions of the null space and the column space should be equal to the dimension of the domain. Then we are saying the dimension of the null space is 2. The domain is three-dimensional, so the column space could be only one-dimensional. Now, is it obvious? If you think, it is fairly obvious, because if you look at the column space of S, it would be a linear combination of the vector 1, 2, 3, 2, 4, 6, and 0, 0, 0. This is actually nothing but a multiple of the vector 1, 2, 3. So the column space, as you can see, has not changed. It is still giving me the same column space that I started with in my original example. So here's an example where I changed the null space but did not change the column space at all. So if you understand these basic ideas behind this, then it will be very easy for us to further understand the theorems associated with it. But now I'm going to show you a better example of how to get the column space for a general matrix. Because up until now, we were just guessing the solutions based on simple numbers. So these were very tailor-made examples.
Should we pause?
Some practical difficulties. Okay, so now we proceed with the non-trivial example where things would be done. So imagine we have this matrix 1, 2, 3, 5, 2, 4, 8, 12, and we have 3, 6, 7, 30. Okay. Suppose you are asked to find the column space of this matrix. We want to see what exactly would it be like. So what is the column space of J? Of course, one can come and say, oh well, column space of J would be basically the linear span of columns of A. Even though that's a very nice description, but it's kind of useless for us. Because it doesn't tell you anything about J. For example, if I asked you, does a vector 2, 7, minus 19 belong to this? There's no way you can tell me just by that description that it's a linear span of the columns of J. So we want better information than this. So remember, we said a vector will belong to the column space of J if this system has a solution. So we will use this idea, and we'll see that we are doing exactly the same thing that we have been doing all along. We could start with the matrix given to us, then we can do a row reduction, and hopefully things will go from there. So B1, B2, B3, we want to know under what circumstances of B1, B2, B3 would this system be consistent. So if you remember, we have to worry about pivot. Pivot should not come into the right-hand side column. That is all we care about. Apart from that, everything else is fine. So let's try to do the row reduction and see what happens. So if I do the row reduction, I will get following thing. So I'm not going to write down the row operations. I'll just tell what the row operations are. So minus 2 times row 1, then added to row 2. So this will be 0, this will be 0, this will be 2, this would be a 2, and this would be a B2 minus 2B1. Likewise, I can take row 1 and try to get zeros in row 3. Minus 3 times row 1 added to row 3 will give me minus 2, and this would be a minus 2 over here, and this would be a B3 minus 3B1. Okay, so I'm kind of doing more than one row operation in one go. Now, it's fairly obvious that if I add the last 2 rows, or strictly speaking, if I take row 2 and add it to row 3, I should get something nice. This would be a 0, all zeros here. And see what I'm going to get over here. I will get B2 plus B3 minus 5B1. Okay. Now, the moment I get this, let's first view a few things before we start finding answers. This was my original matrix J. Okay. What I have got here is the so-called an echelon form of J. Let me denote it by U. So U is the echelon form of J. Of course, I can go for the reduced row echelon form also. So just for the sake of argument, let me go do one more step, even though for our computation's sake it is not really needed. But suppose I divide by 2. This is what I get. B2 minus 2B1. And we have 0, 0, 0, 0. Now we are almost there, we are almost with the echelon form, except that I have to make this entry 0. So if I do one more step, I will get my reduced row echelon form. So it will be minus 3 times rho 2 divided to rho 1, so this will be a 2. And here I will get something nice, or maybe not. It would be minus 2b1 plus 3b2 over 2, which will be a minus 3b2 over 2. Let me redo this. Not making a mistake. So it will be minus 3b2. It's 3b2 over 2. And this would be plus 3b1 plus 4b1. Even though those entries will not make any difference, but what we have got over here is the so-called the reduced echelon form. And as we remember, reduced echelon forms are always unique, so that's an advantage we will have. Okay. Now we will see, getting some answers would be fairly easy for us. For example, if you look at the pivot entry, what are the pivot entries? Here is a pivot out here, and out here we have a pivot. So I'll mark all the pivots in red. So here's my pivot column, and here's my another pivot column. Okay, so there are two pivots which are occurring there. So if I want this system to be consistent, then I don't want any pivot entering here, so that means this entry must be 0. So for consistency, we need b2 plus b3 minus 5b1 to be equal to 0. So this tells me that the column space of J would consist of all those vectors b1, b2, b3 for which b2 plus b3 minus 5b1 must be 0. Now this is a much better description of the column space than what we had earlier, because now we can say that give me a vector and I can tell you whether it belongs to the column space or not. So for example, somebody said, does the vector 1, 1, 1 belong to the column space? I'll just come here and put 1, 1, 1 and test whether it gives me 0 or not. If it does, then it is in the column space. If it does not, then it is not in the column space. So this is the kind of description we are hoping for, but this is not the end of the story. We want to see if we can push our things a bit further. Like, can there be more descriptions of column space which could help us out a little bit? So here's the first question that one may ask. What is the relationship between the column space of J, the column space of U, and the column space of R? Could they be the same? Or there is no relation between them? Any such thing that we can tell? Let's go with an obvious thing. Could they be the same? Can the column space of J be the same as the column space of its reduced forms? So here is the question we are asking. Should the column space of a matrix J be same as the column space of its reduced forms, echelon form or a row reduced echelon forms? This is a common myth that one has to suffer with. But if we look at it a little bit nicely, we should be able to tell whether that is true or not. Look at the column space of R. Look at these columns. They look very nice, but they have one thing in common. All the columns, their last entry is 0. So whatever they span, whatever they cook up, whatever vector is in the column space of R has to have a 0 in the last entry. And if you look at J, would you agree each of these columns by definition should belong to the column space of J? So for example, 1, 2, 3 belongs to the column space of J, but 1, 2, 3 cannot belong to the column space of R or column space of U. So that gives you the answer. Then the column space of J need not be the same as column space of U or R. So here is a concrete reason for us. 1, 2, 3 belongs to the column space of J, but 1, 2, 3 does not belong to the column space of U or the column space of R, because of the last entry being 0. Okay, so question is, does that mean there's nothing useful about finding column space of the reduced row echelon form? No, that's not quite the thing. What it tells us is the number of pivot entries is going to remain the same. So if I come to the reduced row echelon form and I find that there are 2 pivot entries, that means there are only 2 columns which are linearly independent, then I know that those 2 linearly independent columns in my matrix J will be the ones which can span the column space for me. So even though the column space are not the same, but it tells me enough information as to which columns are going to be of help to us.